So we're going to take another look at the second part of the fundamental theorem of calculus, this time using a graph. And so the graph, it says, of a differentiable function f. So this f and this f are the same. This is f of t right here. On the closed interval from 0 to 7 is shown below. So they're giving us the graph of f of t. Now, they're defining h of x as the integral. So what that tells us is we know that when we integrate, we're finding area under the curve. So h of x is going to equal the area under this curve from 0 to wherever we stop. So when I take the derivative of h, if h prime of x is what we're looking for, then remember back up here that h of x was equal to the integral, or h of x was f of x minus f of 0. So if I were to take the derivative of capital F, I just get lowercase f. So h prime of x is just equal to f of x. That's the fundamental theorem, part 2. That's what we learned. And then if I would take the second derivative of h, that would be the same as the first derivative of f. So how does all of that apply to our graph? So what we're saying here is if I want to evaluate from 0 to some point my function h of x, all I need to do is find the area under the curve. And I could do that geometrically in this one. If I want to find the derivative of h somewhere on this graph, then all I have to do is find the actual value of the function at that point. And if I want to take the second derivative, then I would be looking at the slopes of this graph. So here's how it's going to work. They want us to find h of 2. So that means they want us to evaluate this graph from 0 to 2. The integral from 0 to 2. So that just means they want us to find the area. The area from 0 to 2. So back to some geometry here. If I'm going 0 to 2, then I need to find the area of this triangle and this triangle. This one and this one. So I've got that first triangle is 1/2 a base of 1 times a height of 1, 2, 3, 4. And the second one is 1/2 base of 1, height of 1, 2, 3. So half of 4 is 2 plus, and then half of 3, so 3/2. 2 plus 3/2, I get 7/2. That's 4/2 and 3/2, 7/2. Okay? All right. Then they ask us to find the derivative of h at 2. Well, the derivative is equivalent to the function at 2. So all I need to do is go up to my graph and figure out what is the value of the function at 2. So I go over here to where x is 2 and I go up 1, 2, 3. The value of the function is 3. If they ask me to find the second derivative at 2, then they're asking me for the first derivative of f at 2, which would be the slope at 2. And this one happens to be a place where the slope is not defined. That's a sharp turn. Remember, we cannot take the derivative there. So the derivative does not exist. Now, if they had asked me for, like the slope over here at 3, I could do that. I can find the slope of this section, but not here where it's a sharp turn. Okay, so part B, it says write the equation of the tangent line to h of x at x equals 2. Well, they gave us most of everything we need. H of 2, so we need x, we need y, and we need the slope. Well, when x was 2, the function ended up being 7/2. So y is 7/2. The slope would be the derivative of h at 2, and that was 3. So my equation is going to be y minus 7/2 equals our slope m times x minus 2. Okay, the last thing that it asks is what is the domain of h? Well, if we were only look at this, we really couldn't figure that out. But h is defined by function f of t, and f of t is only defined from 0 to 7. So really all you have to do is look over here at the graph. It's defined from 0 to 7. So my domain would be between 0 and 7, or 0 less than or equal to x less than or equal to 7, whichever way you want to write it. So just look at the graph to determine your domain. So the fundamental theorem of calculus part 2 is very interesting when you use it with a graph, because we can find a lot of information just from the graph. We could even, we could write the equation of the tangent line like we did here, or maybe it's just an area under the curve kind of problem. But all of this information can be found if you have the graph.